Okay, a quick video on the comparison test, which causes some confusion. The key with it is, if you know that f of x is less than or equal to g of x, and both of them positive, greater than or equal to 0, for all x greater than or equal to a, then if I look at the integral from a to infinity of g of x dx, and I say that converges, which means the area under g of x from a to infinity is a finite number, then you can conclude that a to infinity of f of x dx converges also. So let's look at what this means. We're saying the area under g of x from a to infinity is a finite number. That's what converges means. Now, if f of x is always less than or equal to g of x, then it has to converge also. So a question gets asked, does this converge? Well, you know in your back pocket that 1 over x squared from 1 to infinity converges. You should know that for anything 1 over x to the 1.01 will converge. So now you'd recognize that this 1 over x squared plus 3 is always positive for x greater than or equal to 1, but it's always less than 1 over x squared. If you have any doubt, plug in 1. This would be 1/4, that's less than 1. 2, 1 over 7 is less than 1/4, etc. So, since we know 1 over x squared from 1 to infinity converges, then 1 over x squared plus 3 dx must converge. So, there's an alternative way of looking at this with divergence, but I want to stay on the convergence for a point. So we know 1 over x squared dx converges from 1 to infinity. We know 1 over x cubed, 1 over x to the 4th. Now I want you also to think about, what about 100 over x squared from 1 to infinity? Now you can't use the comparison test to this on that, but you can think about it. If 1 over x squared dx from 1 to infinity is a finite number, then 100 times it must be a finite number. So you could always say, as I have any constant up here, 5,000 over x squared dx is going to converge. All right.